Physics 1B for September 29th, and right now we're going to be talking about thermal expansion. We're finishing up a couple of details that we didn't finish last time. Then we're going to get into talking about quantity of heat, calories, and calorimetry. So let's just get right into it. So we have a decent amount to cover tonight. So we have this problem right here, where we're going to just review something we did last time. Last time we said that if I have an object that has a length that we call L0, and it's subjected to a temperature change, that the change in length of the objects, when you heat them up, they expand, and this relationship here gives us how that happens. So what I want to do is do a problem that's a little more challenging. This comes from another textbook because I believe that your textbook's problems are just generally way too easy, and I'm pretty sure you have a homework problem that looks just like this. So I thought it'd be a good idea to make sure that we cover it before people get confused. So it says a thermoelectrical short. A poorly designed electronic device has two bolts attached to different parts of the device that almost touch each other in its interior. The steel and brass bolts are at different electric potentials, and if they touch, a short circuit will develop, damaging the device. I don't know why they say that. All this means is if these two objects touch, there's going to be a short circuit, which is going to cause some bad things, okay? But don't worry about that part. The initial gap between the ends of the bolts is 5 micrometers at 27 degrees Celsius. At what temperature will the bolts touch? Assume the distance between the walls of the device is not affected by the temperature change. Okay. So we've got these two objects. We have steel and we have brass. You can see their lengths right here, right? 0.01 and 0.03. The gap between the two of them is 5 microns. And we know that the initial temperature of the system, T0, is 27 degrees Celsius. And the question is, what is the final temperature going to be when the bolts touch? We know we need to use this equation, which means that we need to go and look up the quantity alpha for steel and for brass. And I think those are down here somewhere probably, right? Yeah. So here's our table. We want the linear coefficient expansion. Actually, this probably is getting blocked. Let me move my Discord so I can actually see this. All right, let's get this over here. So for brass, it's 2 times 10 to the negative 5. Degree Celsius inverse. And then for steel, 1.2 times 10 to the negative 5. All right. Now we know that we want to use this equation right here, right? But the question is, how are we going to do it? This question doesn't say, it doesn't tell us the final temperature, so we can't just calculate how far they're going to expand. We need to figure out what the final temperature is going to be when they touch. So does anyone have any idea of how we might go about doing that? We have a few different ideas. People are typing. So delta L is the amount by which it expands, right? We need to find when both delta L add together equal 5 microns. I think that's exactly right, Jordan. That sounds exactly right. So you're saying if we take the change in length of the steel and we add to that the change in length of the brass, that should be equal to 5 micrometers, right? We don't know how much they're going to expand. We know that they both will expand, and since they're both expanding into the same space, we can just say, okay, well, the steel is going to expand by a little bit, brass is going to expand by a little bit. And when they touch, the sum of their expansions has to be 5, right? Does that seem reasonable? Does that make sense to you? Very clever. Okay, so now we just plug things in from here. So delta L steel would be the initial length of the steel multiplied by alpha for steel, the coefficient of expansion, multiplied by delta T, and I'm just going to write this as T final minus T initial plus delta L brass will be the initial length of the brass times alpha brass multiplied by the same temperature change. I guess what you could do here, actually, if you really wanted to, is you could just solve for delta T. But we'll do it this way. You know what? Let's solve for delta T. That's going to be way less mathematics. It'll look better on the screen, too.
The temperature, right?
The change in temperature, yeah.
Gotcha.
Yeah, we're going to solve for the change in temperature. Okay, so solving for change in T, what we'll get is delta T should be equal to 5 times 10 to the negative 6 meters divided by all of this. We'll just copy paste it. Just continue this line. And then we just need to plug all that stuff in. Alright, so delta T equals, so the initial length of the steel was 0.01, that's from the picture. The alpha for steel is 1.2. And multiply that by, oh, you know what? We factored out the delta T, so these aren't here anymore. Sorry about that. This one and this one right here. Alright. Plus, initial for the brass was 0.03. And alpha brass was and then we just plug those in. Can you all tell me what you get if you work that out? I can't quite do this one in my head. It's like 50 over 72 or something like that. Maybe 500 over 72. Yeah, that's right. Yeah, 500 over 72 would be about 7. That makes sense. Okay, so 6.9 degrees Celsius would also be the same thing as 6.9 Kelvin, because the change in temperature is always the same in Kelvin and Celsius. So. All right, just a, thermal expansion problem with a little wrinkle in it. It's not super hard as long as you know what to do. And the key thing to know here is that if I have two objects that are expanding into the same space, you need to take the sum. That's pretty much it. Otherwise, just plug and chug. Any questions? No? Alrighty. Next, we want to do a volume change. Or a change in volume due to temperature. So we didn't talk about this last time, or maybe we did. I don't remember which class I did or didn't talk about things with. But when I have an object that has some volume and it's subjected to a temperature change, the change in volume is given by a quantity called beta times the initial volume times the change in temperature. Looks pretty much like the other equation. One thing to mention about this is that the quantity beta is equal to 3 times alpha. Because if I have something that's expanding in 3 dimensions, and I know that when it expands in 1 dimension, the coefficient of expansion is alpha, well then when it expands in 3 dimensions, it's going to be expanding, this way, and this way, then you're going to get 3 times the coefficient of expansion. And you can prove that mathematically pretty easily too. In fact, I believe your book tries to do it. So in this problem, what we have is a 200 centimeter cubed glass flask is filled to the brim with mercury at 20 degrees Celsius. So we have a flask and it's filled to the brim with mercury. We'll make the mercury green. So right up to the top you have mercury, which is Hg. And we know that it says the mercury is at 20 degrees Celsius, so the initial temperature of our system, we'll write that over here, is 20 degrees Celsius. How much mercury overflows when the temperature of the system is raised to 100 degrees Celsius? The coefficient of linear expansion of the glass is 0.4 times 10 to the negative 5 Kelvin inverse. I just realized something that I forgot. I have class in the morning on the day of our final, not final, of our first exam. I have a 1B class in the morning, and I'll post the lectures obviously to YouTube when I'm done. I'm not saying you have to do this, but if you want to, you could always watch that lecture. You know, you could always watch it on YouTube, or you can come. You can come to class if you want to, if you're free at 9:45 a.m., you know?
I was going to ask what time.
9:45, yeah, 9:45 a.m. on Discord, you know, anybody can come, and I don't know, it might be helpful. I'm not going to tell them anything I haven't already told you, you know, it's not like they're going to have extra information, but, you know, it doesn't hurt, like, I can't, like, okay, I'm getting distracted, let's focus. Alright, so volume change due to a temperature change. How much mercury overflows when the temperature of the system is raised to 100 degrees Celsius? So we also know in this case what the final temperature is. It's 100 degrees Celsius, which means that delta T, which is final minus initial, is 80. So the increase in temperature is 80 degrees Celsius. And they tell us that the coefficient of, this says linear expansion, for the glass, so that's alpha, is equal to 0.4 times 10 to the negative 5 Kelvin inverse. That's alpha, though. This is a volume expansion problem, so we're going to have to use this. Which means that beta, the coefficient for volume expansion, is going to be 3 times this, which is 1.2 times 10 to the negative 5 Kelvin inverse. Something to keep in mind in case problems try to trick you. Pay attention to the words they're using. In this case, it's linear expansion that they gave you. Alright, so what do we need to do? We have to figure out how much mercury is going to overflow when the temperature of the system is increased to this. How do we do that?
Solve for V final, or volume final?
What? Was that it? You want to find volume final? Is that what you said?
Yeah.
I don't know if we can do that or not. Not immediately, at least. Because, well, can we? Yeah, I guess we could, right? So you want to find delta V for both objects? Or, sorry...
I was thinking to find delta V for the mercury, but...
Okay, let's do it first. Let's do that first. Alright, so delta V for the mercury, let's try it, is beta for mercury, which we can look up on that table, times the initial volume. What's the initial volume going to be?
$200 centimeters cubed.
200 centimeters cubed, exactly. So we know that our initial volume is 200 centimeters cubed, and that's because the mercury is filled to the brim, so it's completely filling up this glass. And then we multiply delta T, which we know. So since we have all of the information, we can calculate what the change in volume for the mercury is going to be. So beta for mercury is right there, 18 times 10 to the negative 5. And that is, let's do this one in Kelvin. No, let's not. Yeah, we can, I guess, just to show that it can be done, I guess. So 18 times 10 to the negative 5 Kelvin inverse. The initial volume was 200. And delta T was 80, so we'll put 80 Kelvin. Because remember that delta T in Celsius and Kelvin is always the same. Okay, what's that equal to? $2.88, thank you. Let me see if I agree. So it's basically 16 times 18. Yeah, that's right. Wait. Do you all agree? I mean, it's probably right. I just was trying to do it in my head and don't immediately. Eight plus 6 is 14? Oh yeah, 14 plus 4 is 8. I'm an idiot. Okay, 288. That's right. Alright, so this is the change in volume. And, okay, is that the answer? Is that how much is going to overflow? Are we done?
I have a feeling no. But so I have a quick
Yeah,
question.
I wouldn't ask if we... Yeah, that's right. Go ahead, what's your question?
So, in the book and some of the homework problems, they actually changed delta V into like V final minus V initial, and actually add the V initial to the other side.
Sure.
So, I mean, would you get the same answer, honestly, or?
Yeah, I mean, you'd be talking about different things. Like what you're saying is we can take our initial volume of 200, right? And I can add the delta V to that, right? And we would get 202.88. Is that what you mean? This would just be the final volume then, right?
Yeah, but no, they would basically just, so they would take the delta V basically and say V final minus V initial on the left hand side, and they would go ahead.
You don't always have to do that.
Okay.
I mean, it really just depends on what the problem is asking, right? Okay, so Ariana has the right answer. She says, no, that this isn't the right answer because the glass is also going to expand. That's exactly right. Okay, so the glass expands too. So we also need to take into account the glass expanding, and that should be pretty obvious from the fact that they give us this piece of information right here, but it's obvious. It's not obvious. It's just, that's the hint that supposed to lead you to understand that, oh wait, the glass expands too. So if the glass expands as well, then the glass is getting bigger. And for example, if the glass expanded faster than the mercury, it doesn't. But if it did, then nothing would spill, right? If the glass was always getting bigger and bigger and bigger while the mercury wasn't, then nothing would spill. Some of you were in class on Monday, right? Yeah, like this is the night class. You had to have been. So yeah, I showed you all that demo of like the the ring and the ball, right? Where you expand the ring, expand the ball. Anyway, not everybody saw it though, so it's probably not a good thing to talk about. All right, so change in volume for the glass is going to be, what is it? Beta glass, the initial glass. And then times delta T, we can calculate what that's equal to.
This would be most related like to the ball and ring that you did, right?
Yes, exactly. That's what I was trying to say. This is like a very similar thing, right? Because it's like,
yeah.
Yep. So those of you who haven't seen, I'll show it to you next time.
It just always looks differently when you're calculating,
Yeah,
like, oh,
it's hard to. Yeah, exactly. All right, so we do times 200. We times 80. So here we're going to get, this one's 12 times 16. All right, what do y'all get if you do this one? 6 and 8, 9. This one I think is going to be like 0.292 though. Is that right? 0.192. Oh yeah, because we didn't carry anything. Anything stupid. Okay. So that's delta V glass, and then the total delta V is going to be the base. I would write it in, but I think you all can see it. It's basically the change in volume for the glass minus the change in volume, or from the change in volume for the other one. So we're going to get whatever that is. Can you all tell me what you get? I got it right. Okay, cool. 2.688 centimeters cubed. Very tiny amount. Now, I think in reality, maybe I'm wrong, I bet nothing would actually spill out because of surface tension. Right? Because like mercury can develop a huge, is the right word meniscus? I never know if it's the right word. But the mercury, I mean, it has really high surface tension, so it can really bulge up, right? So depending on the shape of the flask, like if the flask is really skinny, I can see that maybe something would flow over, right? But if you have a really wide flask, then the mercury is just going to kind of like do something like this in reality, right? Right? Don't you all think? Because it's such a tiny amount, right? It's like 1%. Like, can you imagine that 1% of the volume of the mercury might be above the glass? Sure, easily, right? That's not that hard to believe. It's not hard to believe at all. So, you know, this is a physics problem, though, right? So it's not too surprising that it's completely divorced from reality, as most of the problems we do are. And they're usually just about applying some concept, right? It's just the way it goes sometimes. The reality is the problem would be way harder if we had to figure out exactly how much of the mercury would bend up here before it would flow over. So yeah. So maybe it's just a really skinny flask. Sorry if you already answered this, but we don't use the given linear expansion for glass. That's fine. Yeah. So the reason why we don't use this is because this is a volume expansion, and the glass is going to be expanding all around. So like the circumference of the glass will increase, the thickness of the glass will increase. Basically, all dimensions of the glass is going to increase, right? So that's why we have to convert this into the volume expansion. And you do that by using this expression here. Right? Does that make sense why you do that, Kate? All right, I think we're ready to move into new topics. The next thing to talk about is quantity of heat and calories, something that you all probably know a little bit about as it is. Let's start about like calling this the way that the way I learned it. I learned this by talking about the mechanical equivalent of heat. The big question here is, can we quantify heat? Can we make a measurement of how much heat passes from one object to another object? That's our goal here, right? What we know is if I have two objects, and let's say one of them is 20 degrees Celsius, and I place it into contact with a hot object so that they can exchange energy with one another, and let's say the hot object is 100 degrees Celsius, we know that there is going to be heat flow from the hot object into the cold object, right? Because heat is basically a transfer. Oops. So this means transfer of energy from a hot object to a cold object due to a temperature difference. That's what heat is. Now, technically, heat is just transfer of energy due to a temperature difference. This is the real definition of heat, but I always like to remind everyone this is the full definition, right? And this is like my parenthetical piece of it. Because it's just important to remember that you can't have heat go from cold to hot unless you have a heat pump, like a refrigerator, right? That's what a refrigerator does, is it pumps hot air out of the system to make it colder. But that takes a machine. Naturally, heat will only flow in the other direction. And that's what we mean by heat, is a transfer of energy due to a temperature difference, and it always goes from a hot to cold, right? So can we quantify how much heat would be transferred from the hot object to the cold object? The answer is yes. Yes, we can. And the way we know how to do it is because, okay, I should have done a little bit more research before this, but I have such little amount of time between driving home and stuff. So I believe we know this from a scientist named Joule. So Joule is obviously the person who we've named the energy from, or the unit of energy is a joule, right? And I'm pretty sure that this relationship we're about to describe here came from him. I think it came from Joule, an experiment that he did. Now this is an experiment that some of you may have done this before. I know I did it when I was an undergrad, and then when I was in grad school, it was one of the experiments that we had the students do when they took this course, when they took 1B basically. It wasn't called 1B, but we had our version of it, and we would do this lab. It's a really neat lab. So I'm going to try to describe to you how this works here. I'm not going to do it.
Will we be doing a lab similar to it?
We don't have this lab at the school. So this is definitely something that I might probably try to develop because I think it's really neat.
Yeah.
So this is how this works. We have a device where there's some things here that are very familiar to you. This is just a pulley, and this is a mass. This mass obviously has some weight. There's some weight here, right? Actually, I guess that's what that red line's supposed to be. So we'll just say that's the weight of the object. And it's connected via a pulley and a string to something that can rotate here. I would say that there's something missing here, which is hand crank. At least the way we did it. There's probably other ways to do it. It's a hand crank. The idea is that you're going to rotate this around, and this cord is connected to, it's connected around here. Down in the bottom, the thing that you're rotating is connected to a flywheel that can basically spin around. It's just it's a turbine, I guess you might say it, just like a fan, where you're gonna like crank it around like this, and what that's gonna do is it's obviously gonna stir the water. Stirring the water actually kind of a little bit will increase its temperature. I don't know if you all knew that. If you just stir water, you can actually heat it up for the same reason that if I take my hands and I go like this, my hands will get warm, right? Stirring water will heat it up. Not by a lot. Not by a lot. And could you actually measure it? Maybe. Maybe. But there's something else going on here. This rope rubs against this piece right here. And at least in the version of the lab that I did, basically this mass right here is kind of like slipping. Basically this rope slips, but also kind of catches onto the piece right here, this little cylinder. And that means that this connection right here is going to heat up. And what's not made clear in this picture is that this piece, this cylinder right here, has to be an insulator, whereas that purple piece goes straight through and connects to the bottom. So if the temperature of this object increases, the temperature of the water will increase as well. And what you do is you basically, you watch as this object descends through some height, and you try to basically lift it up by cranking it around like this, right? And you watch the object descend by about a meter or so. And you look at the temperature increase, and then you start the experiment again. You crank it, crank it, crank it. You watch the object descend as you're cranking. You try to crank really fast to get the temperature to go up. And then what you do is you can equate the change in potential energy of this object as it falls down through some height, right? There's going to be some height right here, which means you can equate the change in potential energy of the object to the temperature change of the water. So we use the symbol Q to represent heat. And what you do here is you basically equate MGH to the heat increase of the water right here, okay? The temperature of the water will definitely go up, right? And then you just repeat the experiment like 10 times, and you make a bunch of data points, and you try to kind of prove that the heat increase, or the temperature increase of the water is associated with a heat transfer from this crank into the water itself, basically. So the change in potential energy ends up being related to the heat, and then you can actually say, okay, now if I know the temperature change, and I know how much water there is, I can tell you exactly how much energy the water gained, right? And the way that we do that is through the use of a unit that's called a calorie, okay? So 1 calorie is, well, it's equal to 4.186 joules. And the definition of a calorie is that 1 calorie is the heat or the energy needed to raise the temperature of water by, of 1 gram of water by 1 degree Celsius. So there's the mass. You have a gram of water, and if I take a gram of water and I heat it up by 1 degree Celsius, the amount of heat that I've added is 1 calorie of heat. If I take 1 gram of water and I raise it by 2 degrees Celsius, then the amount of heat that's been gained is 2 calories, or about 8 joules. And that's it. I don't know if it's obvious how you would get such a definition from this right here. You know, you have a temperature change, right? You have an energy, so you can connect the temperature change, the mass, to the energy. And that's what we've done here. When they say by 1 degree Celsius, you might be like, well, what about if it goes from 0 degrees Celsius to 1 degree Celsius? Is that any different from going from, I don't know, 100 degrees Celsius to 101 degrees Celsius? And they'd be like, yeah, of course it is. Because if you go from 0 to 1, it might be going from ice to water, right? And if you go from 100 degrees Celsius to 101 degrees Celsius, you're going from water to steam, right? So you want to put this somewhere in the range where it stays liquid. So I think it's from 14. Oh, wait, actually, it's 14.5 degrees Celsius. Who knows why? I don't know. Up to 15.5 degrees Celsius. That's where the calorie is actually defined. How much it differs from other change in temperatures, we don't really worry about in this class, but that's our definition of what the calorie is, right? Now, the type of calorie that you know about, the calorie that's on your like cereal boxes and your sodas and all these kinds of things, or on the menu when you go to McDonald's, is 1,000 calories. So, on food packaging, 1 calorie with a capital C is equal to 1,000 little calories, or 4186 joules. So when you eat something that has 100 calories in it, it has about 4.1 million joules of energy. That seems like a lot of energy, right? 4.1 million joules. 4.1 million meters would be a lot of meters, but 4.1 million joules is not that much energy compared to like what you need on an average basis, right? And obviously, if all of our food packaging had 3 extra zeros on it, that'd be really confusing to people. Right now it always says that a balanced diet is like 2,000 calories a day, depending on your weight. If instead it said 2 million calories a day, that'd probably throw people off. No one likes to do arithmetic with really large numbers. It's never fun. So we simplify things, and we have this new definition of the calorie. And I guarantee if you go back and you look at any package in your home that has calories written on it, it's going to have a capital C. Does this happen on there? No. So, does my Cholula bottle have calories? Cholula has calories, right? Yeah, I don't know if you can see that. Can you see that very well? If we get really close, it's just getting kind of dark. But there's definitely a capital C calorie. And Cholula has 0 calories. Has a lot of sodium, though. Alright. So, 1 calorie, 1,000 calories. Okay, any questions? We call this the mechanical equivalent of heat, basically. You're eating Cholula. Cholula's really good, right? It's good. It's a good hot sauce. Alright. This is nice. This tells us how to transfer energy with water, but we'd like to know, well, how does something like iron heat up? How does something like aluminum heat up? How does something like glass heat up, right? If you're designing an engine in a car that's full of all kinds of components, you're going to need to know how heat affects every single one of those components, right? Is it going to affect the cylinders inside of the engine? Is it going to affect the exhaust pipe? Is it going to affect the transmission? What's going to happen as the entire engine heats up and stuff like that, right? So, in order to do that, we talk about specific heat. Specific heat is a generalization of the calorie. So that's the next thing we're going to talk about here. Who here, prior to entering tonight's class, or I should say prior to taking this class, how many of you have heard of specific heat before? You have, okay. Probably,
what?
Probably this word right here, specific heat. Have you all heard of that before? Probably in 2A. Yeah, you probably talked about it in 2A.
Depends on what kind of topic.
What kind of topic? Okay. So this is what specific heat is. Specific heat is the heat needed to raise the temperature of 1 gram or 1 kilogram of a substance by 1 degree. The heat needed to raise the temperature of 1 gram of any substance by 1 degree Celsius. Now you can imagine that different things heat up at different rates, right? As a really, really simple example, if I take a pot and I put it on the stove, right? So here's my stove. Down here we got some flames or something like that are heating up this object, right? And if inside of here I have a liquid water or something, and let's say I turn my stove on, right? And I let it heat up for, let's say 3 minutes, okay? Let's say I have like a few cups of water in here and I let it heat up for 3 minutes. After 3 minutes, the water is going to be a little bit warmer, right? but the pan will be very hot. Would you all agree? The pan will be really, really, really hot. The water, maybe not so much. It may not even be like 50 degrees Celsius yet. You could probably, after the water being on for 3 minutes, depending on how much water's in there, you probably put your hand in the water, you'd be just fine. You know, I'm not suggesting you should do that. Don't do anything that's dangerous, right? But my point is that water does not heat up nearly as fast as metals do, right? You all agree? Water does not heat up nearly as fast as metals do.
Correct.
Also, water doesn't cool down nearly as fast as metals do, right? How many of you guys have seen Lord of the Rings?
Me.
Is Lord of the Rings a movie that you all seen? At least the first one? I know they're really long.
Yeah.
Okay. You've watched the extended edition? Those ones are really long.
The extended, yeah.
So do you remember the scene at the very beginning when Gandalf like throws the ring in the fire and then he pulls it out and he hands it to Frodo and he says it's quite cool? Do you all remember that? Yeah.
Yes.
If you have a ring and you put it in fire and you pull it out and you wait a few seconds, it will cool down really fast, right? Now, I think in that case it's supposed to be due to some kind of magic, but in reality that's true, right? You know, metals just cool off really fast. They do. So, in order to describe the difference between what's happening with the water and what's happening with the metal, we have a table of this thing called specific heat. And let me show you what the equation is real quickly. So the equation for specific heat is Q. Q, again, is our symbol for heat. I don't know why we don't use H. I feel like they use H in chemistry, don't they? For, like, enthalpy? Is that right? Do they use H for enthalpy in chemistry? Or maybe they use Q. You use Q in chemistry, too, maybe, actually.
MCAT.
Huh? This equation, yeah, you have the same equation in chemistry, right? The MCAT equation, yeah. So this says quantity of heat is equal to the mass of the substance times the C. So C is specific heat. And then obviously delta T is temperature. And specific heat is unique for a substance, and so we've got it right here. Well, here's the, might as well pull the equation up here too. So there's the equation. And here is a list of specific heats for different substances. So over here on the left, you've got the substance, aluminum, beryllium, copper, all kinds of different things. Every type of substance has a specific heat. Aluminum has a specific heat of 910. Water has a specific heat of 4190. And just, you have all kinds of...
Can you explain a little bit about specific heat again? I kind of have a little...
We're still talking about it, yeah. Yeah, no problem. We're going to keep talking about it. I'm going to give you an example so you can understand what these numbers mean. But just notice that they all have different values, right? Which one has the largest value? On the table. Can you tell? Just look at this. Look at this piece of the table here. Which one has the largest value?
Your camera's
blocking. It is blocking it. There we go. Okay.
Water.
Water. Yeah, water. 4190 is the specific heat of water. Okay. And you'll notice that that's pretty close to 4186. Not too surprising. Now, these are given in joules per kilogram per Kelvin. And those are your values right there. So we're going to take a couple of these as an example. Let's use aluminum and iron. Those are good ones, I think. So what does specific heat mean? It means, suppose that I take a block of iron, okay? And just to keep things really simple, let's say I have a mass of iron that's equal to 1 kilogram, okay? And in a separate region where these aren't going to touch each other, I have a mass of aluminum, so we'll just put Al for aluminum, also with a mass of 1 kilogram, just to keep things simple. I'm just going to write down here that the specific heat of iron, or specific heat for aluminum, according to our table right here, is 910. And the specific heat of iron is 470. Iron's Fe, so CFE is 470. So what does this mean? I would argue that it means that iron is going to heat up and cool down much more quickly than aluminum is. And to give you a numerical or conceptual way of thinking about that, let's make this the same color. Suppose that I add heat to both of these objects, okay? Suppose that I take 3 million joules of heat and I transfer it into this object, okay? And then I also take 30,000 joules of heat. I think I might have said a million by accident. We transfer it to this object. How do we do it? Well, we just heat them up, right? Maybe we've got like a blowtorch or something like that, right? And we just, we use a blowtorch and we heat this object up. We use a blowtorch and we heat this object up. And we do it until somehow we know exactly how much energy we're transferring. We're putting exactly 30,000 joules of heat in each one of these. And we look at our equation right here so we can understand what it tells us about the final temperature. Oh, and let's say they start at the same temperature too. So let's say both of these objects have an initial temperature that's equal to 20 degrees Celsius, like room temperature. Which one do you think is going to have the higher final temperature? Is it going to be the iron or the aluminum? What do you think?
Aluminum?
Aluminum, that's right. And it's because it has a smaller specific heat. If we plug the numbers into this equation right here, notice that, so I've rearranged this equation here and just solved for delta T, so it's Q over MC now. Now, since the specific heat shows up in the denominator, that means the smaller the value of a specific heat, right, the bigger the value of delta T is going to be, right? In fact, in this case, we could probably say, since 910 is about twice as big as 470, right, we could call it like 450 and 900. The final temperature for the aluminum should be half of the final temperature of this, or the change in temperature for the aluminum should be half the change in temperature of the iron, right? Does that make sense? And the smaller the specific heat is, the bigger the temperature increase is going to be. And so this allows us, specific heat allows us to talk about energy transfers as long as we know the mass of the substance, the amount of heat that we're adding, and of course we can always look up the specific heat. So you can do it in two different ways, right? Usually you can't really know exactly how much heat you're adding to a system, but what you can very easily measure is delta T, right? It's super easy to just get a thermometer and plug it into something, right? And then find the initial temperature, final temperature. If you know the mass and you know what type of substance it is, you can exactly figure out how much energy was transferred into the system, and that's really powerful. Change in temperature is inversely proportional to the specific heat. That's right, Louis. Yep. Now, what about water? Water has a gigantic specific heat. Gigantic. I mean, it's at least twice as big as any of these numbers up here, except for ethanol, right? It's at least twice as big. So what does that tell us about water? That tells us that water heats up and cools down very slowly. Going back to the example of the pot and the pan, the pot, which is often made of something like maybe aluminum or Teflon or something like this, or stainless steel, the pot always heats up way faster than the water. In fact, water takes a very, very long time to actually boil if that's what you're trying to do with it, for example. This has a major effect on climate as well. If you live near the coast, so around here, if you live in I live in San Pedro, I live like maybe a couple miles from the ocean. If you live in Redondo Beach, if you live in Manhattan Beach, if you live in Huntington Beach, any of these places, or really even if you live in Torrance, because Torrance is still pretty close to the ocean, right? Long Beach, then you probably experience very temperate climate relative to people that live in the Inland Empire, people that live in the valley and stuff like that, right? And that's because the ocean is going to absorb and give heat. So, if you think about it, on any given day, the sun comes up, right? It heats the land, it heats the ocean, right? But the land is going to heat up way faster than the water. Why? Because the land is made of things like asphalt and rocks and cement. Things that heat up really fast, right? You all know when it's really hot outside that the pavement can get extremely hot, right? What about the water, though? The water here in Southern California, especially, it's cold pretty much all year round, right? Isn't that right? It's like always cold, right?
Mm-hmm.
And it's this huge mass of water, right? And so as a result, even if the sun is beating down on the concrete and it's heating up the concrete and yeah, everything's getting hot around here, the ocean is still providing a temperature decrease to the area because all that energy from the ocean, all that temperature, that low temperature from the ocean is going to cool down the air around here, especially as like a breeze comes in from the ocean or something like that and cools things off. And of course, if you go stand right next to the ocean, it's always going to be pretty nice, right? You can really easily see this when you look at like temperature forecasts, right? Weather forecasts. And they talk about, how it's going to be like 70s at the beaches and it's going to be like 90s in the valley. I'm sure you all have heard those kind of forecasts before, right? Or there'll be like a there'll be like a a heat wave that comes through, and they tell people to like be careful, don't go outside and stuff like that, because it'll be like 110 somewhere closer to the desert or whatever. But then where I live, it might only get to like 80 degrees. You'll know what I'm talking about? Does that sound consistent with your experience, right? And that is 100% because of the fact that water has an incredibly high specific heat. It can not only hold a lot of energy, but it can give a lot of energy. So what happens at nighttime then when the sun's not out, right? What happens when nighttime when the sun's not out? When the sun's not out, now the water has actually had its temperature increase slightly over the daytime, right? Because the sun's been beating down on it. And when it cools down at nighttime, the water is actually going to act as a heat reservoir to help heat up the region, right? Because if the temperature of the land gets colder than the temperature of the water, now there's going to be heat transfer from the water back to the land. So that's kind of what ends up happening, and that's why living on the coast is so incredibly nice for having less temperature fluctuations. Does that make sense? And again, it's just because of the specific heat of water. So that's one of the many reasons why coastal real estate is so incredibly valuable. Of course, it's obviously just also really nice to live on the coast because it's beautiful, right? And it's nice to live around the water, but it also makes for very, very temperate climate. Where I'm from, in Oklahoma, there are very few bodies of water. There's rivers and there's a few lakes and stuff like that. But my God, does it get incredibly hot in the summer and incredibly cold in the winter. It's crazy. It gets to like 110 in the summer and it can get below 0 in the wintertime. It's absurd. The temperature fluctuations are insane. And it's largely because it's a landlocked state. There just isn't enough water to like slow down those temperature changes. So when it gets hot outside, it's extremely hot. And when it gets cold outside, it's extremely cold. So anyway, that's specific heat. And we're going to do quite a few problems as examples with this. But now is as good a time as any to take a break. So we'll take our first break here. And we'll come back and we'll do a bunch of the specific heat problems. Does anyone have any questions before we go on break?
Actually,
neighboring? No, sorry.
Go ahead, Andrew. And then we'll go David.
He got it. He can go ahead.
Go ahead, David.
No, it was just unrelated to this, so he can go first.
Yeah, I actually have a question on the homework problem. One of the homework problems actually brought up that stress can actually be negative.
What? Stress? Yeah.
Yeah. Stress can actually be negative. I mean, what's an example of that? Is it like when they're trying to like basically collide and go into each other? Is that when it's going to be negative? Or
is that one of those problems where you have like two objects and they're like fastened to something on both ends, and then the object cools down, so the object is like it's like pulling in on the objects?
No, this problem was train tracks. So I brought up train tracks, and basically, let's suppose like the train tracks were. I got the exercise number. No, it's actually I don't have the exercise number, but I mean I have the question itself. So, I mean it says they're originally in contact, and like what is the stress on a summer day when the original temperature is 32?
Well, all I'm going to tell you is that because the definition of stress has a delta L inside of it, right? It's like delta L over L naught, right?
Yeah, delta L.
So if delta L is negative, then the stress will be negative. You don't remember which problem it was, so I can pull it up here? I'll let you look at it. Maybe we'll talk about it after the break.
Actually, I believe it should be like 1724, 1721.
Yeah, we have to take a break, but I'll try to answer your question.
And I can ask you this after class.